Hey guys, this video is going to be on program structure and commonly used codes. We've already gone over G90 absolute programming mode and G91 incremental programming mode. We've also talked about G codes on how they are cutting and movements, and M codes, how they are on-off function and on-off and miscellaneous functions. So going forward, this is going to be on commonly used codes. We're going to talk about safety lines in the beginning of our program, and getting into can cycles for drilling and spot drilling. When writing our programs, it's very important that we need to begin and end with a percent sign. This is going to mark the beginning of our program, and it's going to mark the end of our program. Okay? So after our percent sign, which communicates where the beginning and the end of the program is, we're going to have a program number. The beginning of the program number is with the letter O, not a zero, letter O. And then a 5-digit program number will be accepted into the controller. 1, 2, 3, 4, 5. All right, this will determine where the program lands in the program list in the controller, and you'll be able to search for it in the program list. You can pull up the program number, but this is how it's going to fall into the controller by this program number. And it begins with the letter O, not 0. All right, so we have our program beginning. We have a percent symbol, which is going to communicate the beginning of the program. And then we have our program number, beginning with a letter O and then a 5-digit number after that. This is where our program will fall within our program controller. There will be a list of programs depending on if they're all saved. There could be multiple programs in the controller, and whatever this 5-digit number is right here is how the controller will sort out the program numbers. Right. The next line is a little bit of difference in opinion on what comes next, but for our class and going forward with how we're going to write programs, we're going to have a safety line. All right. These commands will be at the beginning of every program, and this safety line will ensure that we're in the correct programming mode, measurement system, coordinate plane, and will cancel any cutting actions to prevent any crashes or unnecessary cutting. Our safety line will come next. This will be in every program. So the 5 codes that we're going to use in our safety line are going to be G90, G20, G17, G40, and G80. I'm going to get into a little description about what each of these codes mean and why they're important, and then we'll continue on with our program. All right, so our safety line is going to contain these codes, and it will be at the beginning of our programs. These codes are going to ensure that we're all in the right programming mode, measurement system, coordinate plane, and cancel any cutting actions. So these 5 codes, starting with G90, is going to put us in absolute programming mode. We talked about this earlier in our video 1. This is going to be working from a fixed 0. G20 is going to verify that we're working in inches. Working in inches. If you wanted to work in metric or needed to work in metric, this would be G21 for metric. So our first two codes, G90 tells the machine that we are in absolute programming mode, working from a fixed 0. And G20 is telling the machine that we're working in inches. Now G17 allows for circular motion in the XY plane. This may not make sense at the moment, but when we get more into cutting actions and we get into circular interpolation, G17 is going to be very important that we have that on, because our cutting tools will be making arcs and radii, and we got to make sure that we are in the XY plane. Okay. Page 56 in the Haas programming text gives a good picture of the motion of G02 and G03, which is circular interpolation. And we got to make sure that we're going to be in the XY axes for cutting contours and the Z plane for infeed. Okay, so G17 is important for circular motion. And it's going to be very important when we get into circular interpolation, codes G02, G03, and page 56 in our Haas textbooks, our Haas programming text will give a good picture of it. Programming text. Next code here, G40. What is that about? G40 is going to be cutter compensation cancel. Cutter comp cancel. Now, cutter compensation is used to offset the center of the cutter and shift the distance of the radius. These are codes G41 and G42. We're going to cover those in a couple weeks, but it's important that in the beginning of our program in our safety line that we cancel this. So we're going to call up G40 and it's going to cancel cutter comp. This will make more sense once we get into cutting actions and cutter compensation. But we want to make sure in the beginning of our program, before we turn anything on, that it is turned off. And our last code of our safety line is going to be G80. And this is canned cycle cancel. Canned cycles are Z-axis repetitive operations, such as drilling, tapping, and boring. These cycles are going to be active until canceled with G80. So at the beginning of our program, we want to make sure that we turn everything off because we don't want any unnecessary cutting. So this is canned cycle cancel. And canned cycles are Z-axis repetitive operations. And we're going to have these after our canned cycles of spot drilling and drilling. But in the beginning of our program, on our safety line, we got to make sure that we turn everything off in the beginning of our program so there's not any unnecessary cutting or movement in that Z-axis. All right, so we start off our program. We have our percent symbol, we have our program number, and then we have our safety line. All right, the next code that we're going to be selecting is going to be for our work coordinate offset system. All right, so in the beginning of starting up the machine, all three axes are going to be moved to an extreme positive location until the limit switches are reached. So you walk up to the machine, you turn it on, and the machine's going to be is going to ask you to home the machine. So when you home the machine is going to move to these three axes, X, Y, and Z, at the extreme positive locations until the switches are hit. All right. Now, that's normally going to be in this top right corner over here. Okay. So if you're looking down at the machine from a bird's eye view, you have your workpiece here in the center, right here, sitting in a vise. If you're looking down, the machine is going to go all the way back in the Y positive. It's going to go all the way over in the X positive, and then it's going to go all the way up in the Z positive, to home the machine at its limits. It's going to be in the very back right corner. All right. Well, that is the machine's home position. But when we're working with a workpiece and say we want to edge find here and here, we're going to be telling the machine a new 0. So the machine's home is 0, 0, 0 up here. But we are going to relocate 0 to over here. And to do that, we need to call up a G code to tell the machine a new work coordinate system and a work 0 offset. So we have homed the machine, and now we need to tell the machine our new work coordinate system after we edge find our workpiece. So we home the machine, our workpiece is in the vise, we have an edge finder in the spindle, and then we go to find this top left corner of we want to make this our new 0, 0. So there's 6 work coordinate offsets that can be used. G54 through G59. Now we're going to be using G54 for our programs, and that's going to go on our third line of our program. G54. This is our work coordinate system. So now that we have a G54 in our work coordinate system, we are setting our offsets and changing the machine 0, 0 to a new convenient 0, 0 for us to work off. Now we're working off this corner. So we have now reset and told the machine what our 0, 0 will be in a work offset in the work coordinate system by using a G54 code. Right? This is very important to have. I like to put this on its own line in case you need to change your work coordinate system to a different G number. It'd be G55 maybe, or G56 or G57. So having it on its own line allows you to make a quick edit in your program on its own single line. So I like to separate it. Some people like to put it up here on the safety line but I like to have it on its own. So if you need to edit it for whatever reason, you can edit it quickly on its own line, right? So we have the beginning of our program with a percent symbol. We have our program number, our safety line, and now a work coordinate system. The next thing we can do is call up a tool. So this is going to be called up with an M code. I like to write it as following: M06T1. So M06 is a tool change command. And T1 would be tool 1. So we're telling the machine to go into the automatic tool changer and pull up tool 1. Now the spindle will stop. The Z axis is going to move up to the machine 0 position, and it's going to grab and put whatever tool you call out into the spindle. Now, so things are starting to come together with G codes in our safety line, our work coordinate system, and calling up a tool change. Once a specific tool is in the spindle, we will move to location. This is going to be a G00. This is a rapid movement. And this rapid movement is going to be a non-cutting movement and is used for a quick position to a location for cutting or for clearance. So let's say we go to X0, Y0. So we use our safety line. We tell the machine that we are in absolute programming. We are in inches. We're in the XY circular plane. We have canceled cutter comp. We have canceled any can cycles. We have reset our 00 for our program using G54. Called up tool 1, and we are rapiding to location X0, Y0. So our program now looks like the following. We start having several G codes in there. These are very commonly used codes, and we have some M codes in there, and we're starting to move around, call up a tool, and we're starting to get things in motion. Now, when we put this program together, and we plug it into the machine, everything is going to be moving very quickly when the program kicks in. It's going to jump line to line to line. It's going to perform any cutting operations that you call out, right? So we're going to get used to writing these out line by line, taking our time. But when we put everything all together, things are going to move quickly in the machine or at the machine. So we have called up tool 1 and we have moved the location. Next thing we're going to do is turn on our spindle. This command is going to be M3, and then with an S and whatever speed you want the spindle to go, right? So M3 is spindle on clockwise. And whatever speed we want. So let's just put 1,000. All right, we've called up tool 1. We've moved to location X0, Y0 in our G54 work offset, and we've turned the spindle on clockwise at a speed of 1,000. Right. So after that, we now have to tell the tool a Z height offset, right? So we have told the machine an XY offset, we now need to tell the machine a Z offset, and this will come in this line here. I spoke earlier about how the machine 0 is in that top right corner of the machine. If we're looking down at the machine, here's our work. The machine 0 will be up here, right? Top right corner. And the Z is going to be at the highest point of the machine that it can travel. Well, we need to bring the tool down to our workpiece, and we need to tell the machine a Z offset from the machine 0 to our workpiece. And this will be G83. This is our tool length compensation. All right. So once again, during each setup, we're going to be installing tools in the machine, and we are going to be touching them off to the top of our workpiece, setting a part 0, a Z part 0. From that position, a tool offset will be recorded, telling the machine the distance to compensate in our Z from the machine 0 to our workpiece. Now, G43 is going to compensate from machine 0 to our workpiece, and then we're going to give it a Z height. So we'll say Z 2.0, and we have to give the machine an H value, and we're going to go over this in lab. But when we set up our tools in the tool offset page, there are height values for each tool. So in our program is communicating what tool we're using, say tool 1, and what offset, Z offset, it needs to recognize to compensate that height. So whenever you call up a G43, you want to give it a Z height to go to, but you also have to call up an H value for the machine to communicate what tool that you're offsetting. In this case, since we're using tool 1, we're going to be using H01. Now, if you had tool 2, that H value would be H02. So this H value is always going to match our tool. As you get into more complicated machining and with several tools, if you have tools set up at a known height, I suppose you could have different H values for different tool numbers, but for learning and education purposes, we're always going to have the same H value as the tool number. So tool 1, H01, tool 2, H02, tool 3, H03. Because we're going to be setting up our tools, say tools 1, 2, and 3. We're going to be installing them into the spindle, moving them down with the hand dial, touching them off to the top of our tool, the top of our workpiece, and the length of hangout of each tool will almost certainly be different per each tool. And this code, G43, is going to communicate that offset and the difference of length from the machine 0 to the workpiece, and this H value is going to match our tool number and our offsets. And we'll get more into this in the lab, and we'll be using the simulators to set everything up and get you guys familiar and used to setting up tools, and you'll see how the H values correspond with the tool numbers. So our program looks like the following. I hope this is a little bit neater. I changed over to text instead of drawing this out. But this is how our program now looks, and we are now ready for cutting operations. We can begin with drilling can cycles, which are commonly Z-axis repetitive operations. So our can cycles are going to be Z-axis up and down motions. And for our first cycle, we're going to be using G81. We're going to use G81. This is a straight drilling cycle. And we're going to be using this for spot drilling. All right. So we're going to call up this code. We're going to give it some settings. We're going to give it locations. And when we run this cycle, the G81, the machine is just going to go down to a programmed Z depth and come back up and then move to the next location. This is a straight drilling cycle, G81. We'll be using it for spot drilling. And we're also going to be using a G83, which is peck drilling for actual holes. We're going to give this code some commands, and it will peck and retract at a certain feed rate, going to a program Z depth. All right, so resuming with our program, if you look here, you can see that I have a few other lines added. Right, so we ended off with our G43, our tool height compensation. Then I put in here an X and Y coordinate, and I added some variables to our G81 code, our straight drilling cycle that we're going to be using for spot drill. All right, so starting off with the X and the Y location. All right, so before we can start drilling, we need to be at our first location to begin our cycle. So I'm looking at mill part 1. Okay, so I have a G99 set in my straight drilling parameters. The G99, and it's got me retracting to the R plane of 0.1. I've chosen a Z depth of 50 thousandths. That means in our straight drill cycle, we're just going to go down 50 thou and then retract to 100 thou above the workpiece. And this F 3.0, this is going to be our feed rate for the drilling cycle. How I got that number, and I will get you guys a formula worksheet, is inches per minute equals inches per rev times RPM. Okay, the standard milling machines operate in inches per minute, so we need to convert an inches per revolution to inches per minute. Okay, so I have a handout for various drill speeds for inches per revolution. We're going to use 3 thou in this example. So we would have inches per minute equals 0.003 times the RPM that I've chosen, which is right here. So this is going to be 1,000. We do our multiplication, in inches per minute will be 3.0. So that's a little conversion there. And this is going to be our feed rate. And it will go right there. This will be the same thing for our peck drill cycle once we get there. If I were to start drilling this, I'm going to be starting down here in the bottom left, right here. So I would set up my work coordinate system in the bottom left corner. That's where all of the dimensions are coming from. So I'm going to start off in the bottom left corner. It's going to make programming my points easy. So my first point is at x.5 and y.5. So we need to be at our first location before we can begin the can cycle. And we could start at 0, 0, but it's going to, the machine is going to attempt to drill a hole there. So we want to be at our first hole location and then call up our can cycle. In this case, it's G81, and the cycle is going to begin at whatever location is on the previous line above it. So if we did not have this, it would start its drilling cycle at 0, 0. But we do have it. So we have x.5, y.5. All right. So what does the rest of these variables mean? G99, R, Z, and F. All right, so we are at our first hole location. The x.5, y.5. Then we're going to call up our straight drill cycle that we're going to be using for spot drilling. We call up G81. And then the following code, G99, is going to determine a plane for the tool to retract to. There's two different codes we can have here, G98 and G99. You can see that I'm using G99. G99 is going to retract to an R plane. Retract to R plane. In our case, the R plane is 0.1. All right. If we had G98, this will return to the initial clearance plane. So what does that mean? That means that if we have G98 turned on, that we're going to be moving after each drilling motion back to whatever Z height we have previously set in our program. In this instance, it would be Z 2.0. Now, so the G98 returns to a clearance plane, which can be very helpful if you need to jump or hop over bosses or features that you could crash into. So if you have fixturing holding down your workpiece or a work plate, and you need to jump over, say, a toe clamp or some other fixture, you could use a G98 to return to Z 2 inches above the workplace and then move over to our next location. For our program, we are using G99. We're just going to have a plate sitting in a Kurt vise, and we can retract to 0.1 above the workpiece. We have nothing to hop over. We don't have any clearance issues. and we don't need to waste time by going up in the air each time before cutting. So G99 will return to the R plane, which we have set in our program line. G98 would return to a clearance plane previously set in the program. If we didn't have G99 R1 and we had G98, we would go back to 2 inches above the workpiece. I have a very helpful handout that I will be posting on Blackboard, and we can go over it in lab the following week. So now that we have established what plane we're going to retract to, G99, we're retracting to the R plane, we need to give a Z depth for our straight drilling cycle. So I have chosen 50 thousandths right here, which means that our tool is going to go down 50 thousandths and then come up to 0.1 above the workpiece and then move to the next location. Okay, so I have a G99 set in my straight drilling parameters. The G99, and it's got me retracting to the R plane of 0.1. I've chosen a Z depth of 50 thousandths. That means in our straight drill cycle, we're just going to go down 50 thou and then retract to 100 thou above the workpiece. And this F 3.0, this is going to be our feed rate for the drilling cycle. How I got that number, and I will get you guys a formula worksheet, is inches per minute equals inches per rev times RPM. Okay, the standard milling machines operate in inches per minute, so we need to convert an inches per revolution to inches per minute. Okay, so I have a handout for various drill speeds for inches per revolution. We're going to use 3 thou in this example. So we would have inches per minute equals 0.003 times the RPM that I've chosen, which is right here. So this is going to be 1,000. We do our multiplication, and inches per minute will be 3.0. So that's a little conversion there, and this is going to be our feed rate, and it will go right there. This will be the same thing for our PEC drill cycle once we get there. After we set these parameters of G99, the R plane, and a Z depth and a feed rate, we can continue plotting our points for us to complete this project. So if you look at our drawing, I'll do 3 more holes. I'll do the 3 holes here on the left. So our second hole is going to stay in the X 0.5, and it will go to Y 1.25. So this will be X 0.5, Y 1.25. Our next line will be X 0.5, Y 1.75. X 0.5, Y 1.75. And then the last hole in the top left will be X 0.5, Y 2.5. X 0.5, Y 2.5. So that this would spot drill these 4 holes. Now we start off at our first location before the can cycle. Which would be right here. Here is our first location. We call up our can cycle, straight drill. For spot drilling, and then we list our points that we want to continue to cut. So that's second hole, third hole, and the fourth hole. Okay, so I know there are more features on here. It's like there's 12 more holes, the total of 16. I want you guys to continue to do this. You would just keep listing the XY coordinates underneath here. So once all of our points are finished being entered into our program, our next line is going to be to cancel the can cycle, which is, if you remember up here, it's going to be G80. So we will call up G80, and then we can wrap it to a safe position away from the part. So we'll just go Z 2.0. Then we can turn off coolant if we turn it on, which we did not in this program. And then, well, we can stop the spindle, M5. And then we can call up our next tool. So this is going to be spindle stop. And then we can call up our next tool, which would be M6T2. Tool change, tool 2. So when we do that, the machine is going to move up in the Z axis and then go to the automatic tool changer and change our tool. So once we finish entering all of our points, we need to wrap up this portion of the program. If you guys remember, we called up in our safety line G80, which is the can cycle cancel. So that's what we're going to call up after all of our points are entered. We're going to cancel the can cycle, G80. Then we can move to a safe Z location, away from the workpiece. We'll go to Z 2.0. And then we'll call up an M5 code, which is a spindle stop. And we can call up our next tool. So if you guys recall, tool change is right here. So we will call up our next tool, which would be M6T2. Tool change, T2. Okay. So after calling up T2, tool 2, we can fall in line with the beginning of our program again. Now, the safety line and the work coordinate system are not necessary down here. Okay, so this stuff here is not necessary for tool 2. It's already been established in the program. After tool, that did not come out right. After tool 2. Okay. So how this program will continue will be the following. Okay, so continuing on with our program, we have done our tool change. We now have tool 2 in. So we're going to move over here. So these lines right here, these would fall underneath the M6T2. Okay, so this would all just list from top to bottom. I just ran out of space, so I moved it over. Right, so you can see that I have rapided to my first hole location. All right, first hole. I turn on the spindle. Okay, spindle on clockwise. I call it my G43 with an H02. Very important. And then I call up my peck drill cycle. All right, so this is what all this information means. G83 is peck drill. G99 is going to be the R plane. The R is whatever retract plane we want to move to within our cycle. I have 0.1 above the piece. Q will be our peck value. So as this drill is going into the hole, is going to peck at 50 thousandths increments to a total Z depth. I chose negative 460.460 with a feed rate of 3.0. That is inches per minute. That is what standard milling machines operate in. And if we need a reminder of the formula for that, this is inches per minute equals our feed per revolution That's feed per rev times RPM. Okay, so our feed per revolution, which I have that handout to give you guys. In this instance, I'm using 0.003 times our RPM. In this example, I used 1000. So to convert feed per revolution to inches per minute, you multiply these and I got 3.0. So after our G83 line, we will just continue to plot our points like these. So you will have a list of points under your G83, and then you will write a G80 code after your last point. You'll do a Z 2.0. We'll put a rapid in there. Should be a G00 Z 2.0. we will turn off the spindle, and then we will conclude our program with the percent sign. That is going to wrap up a simple drilling program. Hope you guys were able to follow along. If you have questions, shoot me an email. We're going to discuss this further in lab, and then we're going to pull up the simulators and start setting up tools and going through the motions of loading up the program, setting up our tool offsets, our work coordinate system, and seeing how the program runs. So, like I mentioned, if you guys have any questions, reach out to me, and I'll see you guys in lab.